Wormholes, theoretical passages through space-time that could create shortcuts for long journeys across the universe, have captivated scientists and the public alike. Often depicted in science fiction as tunnels that connect distant parts of the universe, the concept of wormholes is rooted in the complex field of general relativity and quantum mechanics. This essay delves into the scientific theories behind wormholes, their potential implications, the challenges they present, and the ongoing research in this intriguing area of physics. Theoretical foundations. General relativity and the Einstein-Rosen bridge. The concept of wormholes is closely tied to Albert Einstein's theory of general relativity, which describes how massive objects warp the fabric of space-time. In 1935, Einstein and his collaborator Nathan Rosen proposed the idea of bridges in space-time, now known as Einstein-Rosen bridges or wormholes. These bridges theoretically connect two different points in space-time, creating a tunnel-like structure. Schwarzschild Wormholes. The simplest type of wormhole is the Schwarzschild wormhole, derived from the Schwarzschild solution to Einstein's field equations. This solution describes a non-rotating black hole and suggests the existence of a tunnel connecting two black holes, one in our universe and one in a parallel universe. However, Schwarzschild wormholes are not traversable, as they would collapse before anything could pass through them. 1.3. Traversable wormholes. For a wormhole to be useful for travel, it must be traversable, meaning it remains open long enough for matter to pass through. In 1988, Kip Thorne and his colleagues proposed a theoretical framework for traversable wormholes. They suggested that exotic matter with negative energy density could stabilize a wormhole, preventing it from collapsing. This concept remains speculative, as exotic matter has not been observed in nature. 2. Exotic matter and negative energy. 2.1. Exotic matter. Exotic matter is a hypothetical form of matter that possesses negative energy density and negative pressure. In the context of wormholes, exotic matter is crucial for keeping the wormhole throat open and preventing it from collapsing under its own gravity. The existence of exotic matter is one of the biggest challenges in making traversable wormholes a reality, as it has yet to be discovered or created in a laboratory. 2.2. Casimir Effect. One potential source of negative energy is the Casimir Effect, a quantum phenomenon that occurs when two uncharged parallel plates are placed very close to each other in a vacuum. The Casimir Effect generates a small attractive force between the plates, which can be interpreted as the presence of negative energy density in the vacuum between them. While the Casimir Effect is a real and measurable phenomenon, harnessing it to stabilize a wormhole remains purely theoretical. 3. Wormholes and quantum mechanics. 3.1. Quantum field theory. Quantum field theory, or QFT, provides a framework for understanding the behavior of particles and fields at the quantum level. In the context of wormholes, QFT suggests that vacuum fluctuations or temporary changes in the amount of energy in a point in space could play a role in the formation and stability of wormholes. These fluctuations could potentially create or destroy wormholes on very small scales, a concept known as quantum foam. Stephen Hawking's work on black hole radiation, known as Hawking radiation, also has implications for wormholes. Hawking radiation arises from quantum effects near the event horizon of a black hole and suggests that black holes can emit particles and gradually lose mass. If wormholes share similar properties with black holes, they might also emit Hawking radiation, affecting their stability and longevity. So let's dive into the potential applications and implications of wormholes. One of the most exciting potential applications of wormholes is faster-than-light travel. If traversable wormholes exist, they could theoretically allow for instantaneous travel between distant points in the universe, bypassing the speed of light limitation imposed by special relativity. This could revolutionize space exploration, making interstellar travel feasible within human lifetimes. 4.2 Time travel. Wormholes also offer intriguing possibilities for time travel. By manipulating the mouths of a wormhole, it might be possible to create a time difference between the two ends, allowing for travel into the past or future. This concept raises numerous paradoxes and challenges, such as the famous grandfather paradox, where a time traveler could potentially prevent their own existence. 4.3 Communication across vast distances. In addition to travel, wormholes could provide a means of instantaneous communication across vast distances. Signals sent through a wormhole would arrive at their destination without the delay imposed by the finite speed of light, facilitating real-time communication between distant parts of the universe. 5. Challenges and obstacles. Third, 5.1 Stability and exotic matter. The primary challenge in making traversable wormholes a reality is the need for exotic matter to stabilize the wormhole throat. Without a known source of negative energy, creating and maintaining a stable wormhole remains purely theoretical. 5.2 Energetic requirements. Even if exotic matter were available, the energy required to create and maintain a traversable wormhole would likely be enormous, potentially on the order of the energy output of entire stars or galaxies. This presents a significant practical obstacle to the construction of wormholes. 5.3 Quantum effects and instabilities. Quantum effects such as vacuum fluctuations and Hawking radiation could destabilize wormholes, causing them to collapse or evaporate. Understanding and mitigating these effects is a major challenge in wormhole physics. Current research and theoretical developments. String theory and extra dimensions. String theory, a theoretical framework that describes fundamental particles as one-dimensional strings, offers potential insights into the nature of wormholes. In some versions of string theory, extra dimensions beyond the familiar 4, 3 spatial and 1 temporal, could allow for the existence of stable wormholes. Research in this area is ongoing and highly speculative. Quantum gravity. A complete theory of quantum gravity, which unifies general relativity and quantum mechanics, is essential for a full understanding of wormholes. While no such theory currently exists, approaches such as loop quantum gravity and the holographic principle offer potential avenues for exploring the quantum aspects of wormholes. 6.3 Numerical Simulations. Advances in computational power have enabled detailed numerical simulations of wormholes and their properties. These simulations help researchers explore the behavior of wormholes under various conditions and improve our understanding of their stability and potential observable effects. 7. Observational evidence and detection. 7.1 Indirect evidence. While direct evidence of wormholes remains elusive, researchers have proposed several indirect methods for detecting their presence. These include searching for anomalies in the motion of stars and galaxies, gravitational lensing effects, and unusual signals that might be indicative of a wormhole's influence on its surroundings. 7.2 Gravitational waves. The detection of gravitational waves, ripples in space-time caused by massive accelerating objects, offers another potential method for identifying wormholes. If a wormhole were to form or interact with a massive object, it could produce a distinct gravitational wave signature that might be detectable by observatories such as LIGO and Virgo. 7.3. High-energy astrophysics. High-energy astrophysical phenomena, such as gamma-ray bursts and active galactic nuclei, could provide clues about the existence of wormholes. Observing unusual patterns or inconsistencies in these phenomena might suggest the presence of a wormhole or other exotic structure. Philosophical and ethical considerations. Implications for causality. The potential for time travel through wormholes raises profound questions about causality and the nature of time. If time travel were possible, it could create paradoxes and challenge our understanding of cause and effect. Philosophers and physicists continue to debate the implications of these possibilities. Ethical considerations. The creation and use of wormholes also present ethical considerations. The potential for faster-than-light travel and time travel could have far-reaching consequences for society and the environment. Ensuring that these technologies, if they become possible, are used responsibly and ethically will be a significant challenge. Conclusion. Wormholes remain one of the most intriguing and speculative areas of theoretical physics. While they are rooted in the well-established framework of general relativity, their existence and properties are still largely theoretical. The challenges of exotic matter, energy requirements, and quantum effects present significant obstacles to the realization of traversable wormholes. However, ongoing research in quantum mechanics, string theory, and quantum gravity continues to push the boundaries of our understanding. As we advance our knowledge of the universe, the study of wormholes may one day move from the realm of science fiction to that of science fact, opening new horizons for exploration and understanding.